All right, and so that matches up. I didn't hit the record button right away, and so Jordan went down to grab his dynamics textbook, and he found the equation for rho, and so it would be the inverse of what's shown here. Is that correct, Jordan?
Yep.
All right, and so I kind of like pointing you back to that reference in your dynamics textbook to kind of see how that all fits together. All right. And so next up is, I need to get my windows all squared away. I think, yeah, we're right here. And so next up is the more common approach to solving these beam type problems, where you solve for your internal moment as a function of x and then integrate back only twice and then use your boundary conditions from there. And so this is a cantilever beam with a point load on the end of it. And this is really a common scenario that comes up a lot for beam bending, and is probably one of those that, unlike the previous ones, this one you probably more want to commit to memory in terms of the deflection at the end of the beam, because it comes up so often in different things. But if we look at that, we have shear that's going to be occurring at the end of the beam, and supporting moment as well, since it's a fixed support. And so if we solve for our reaction forces, summing moments about A here, we'd have a minus P times L minus an MA is equal to 0, which just tells you MA is equal to a minus PL. It would be acting in the opposite direction. And summing forces in the Y, you'd have VA minus P is equal to 0, which just tells you that VA is equal to P. And then if we draw a free body diagram over this first half, or given distance x over, we can figure out what our internal moment and shear is. And that's really what we're after, is the internal moment as a function of x. And in this particular case, there's no loading in the span of the beam. There's no other boundary conditions, so that moment as a function of x is going to be valid for the entirety of the length of the beam from x equal to 0 to x equal to L. And so that makes this problem nice to solve, and that we don't need to do it over multiple segments. And so that free body diagram, again, we kind of keep VA and moment at A defined in their positive definitions, even though we saw that it acted in the opposite. We'll just keep the sign included throughout the analysis. Given the distance x, its positive internal shear and moment are going to be a function of x. And so as we go through that, summing forces in the y, we have v of a minus v as a function of x. And it's only going to be for this problem that we define then that as a function of x. Normally, we just call that v1 or v2 because we're multiplying things by x2, and that just causes things to get confusing. And so I just wanted to keep it in this first example, just understanding that these are functions of x. And so here, v of x is just going to be equal to v of a. And we already saw v of a is equal to p. So v of x is a constant, just equal to the load p throughout the length of the beam. So this one is a constant. It's not a function of x, but there are cases where that could be a function of x. And then the summing the moments about the cut, you would have mx that's the moment as a function of x, minus VA times x minus MA is equal to 0. And so the moment as a function of x is equal to VAX plus MA. And M of x, then V of A is equal to P. M of A is equal to minus PL. So we end up with P times x minus PL. And it's just telling you what that moment is as a function of x. And that's where we can then start in the center point of those system of 5 equations. And we only have to deal with 3 of them. EI is equal to d squared V dx squared is equal to your moment as a function of x. And we just solve for that as px minus pl. So that's now where we get our expressions now as a function of x. And we can relate it back to the loading and the length of the beam. And now you can solve with your boundary conditions. We have EI dv dx and integrating px minus pl with respect to x. We end up with EI dv dx equal to px squared over 2 minus a plx plus c1, our constant of integration. And if we integrate back again, we have EI vx is equal to a px cubed over 6 minus plx squared over 2 plus a c1x plus c2. And so we have our 2 equations now for our slope and for our elastic curve, v as a function of x. And so it's the same process. We just only had to integrate back twice because we weren't relating anything to the internal shear or the distributed load at all. We based everything back on the internal moment as a function of x. And boundary conditions, they still apply. And so at v equal to 0, the displacement is equal to 0. And so if we plug that in, that's going to cause C2 equal to 0. We know the slope at 0 is equal to 0. So back here in this top expression, everything's 0 except for C1. So we know that C1 is also equal to 0. And so our elastic curve is just going to be v of x equal to px cubed over 6ei minus plx squared over 2ei. Both C1 and C2 are 0. But one of the things we might want to solve is the slope at L and the displacement at L. And so if we go back to our first expression way up here, dv dx is equal to our slope is equal to p over 2ei x squared minus 2lx. And then if we substitute L in for that, we'll have an L squared minus a 2L squared will give us a minus L squared. And so we end up with theta of L is equal to minus PL squared over 2EI. And one thing I don't know if I mentioned that about the slope, this will be defined in terms of radians. We'll have Young's modulus is a unit of force per length squared. So we'll have length to the 4th on the top, length to the 4th on the bottom with the area moment of inertia and the load canceling. So it will be unitless, but that will be in radians. So that's the slope at L. And then if we look at the displacement, again, that v of x, when we move e over ei to the other side, we end up with p over 6ei times the quantity x cubed minus 3lx squared. And so plugging in L for that, finding the displacement at that free end, p over 6ei times L cubed minus 3L cubed. And we have 1 minus 3 will give us a minus 2 PL cubed over 6EI, which is a minus PL cubed over 3EI. The 2 will cancel with 6 to give you 3. So this is the expression that I mentioned that you should remember, is what the tip displacement is for a cantilevered beam with a point load. And that's PL cubed over 3EI. And the negative just signifies that that's going to be a displacement downward in the vertical direction. And so you could then solve based on your elastic curve, what is the displacement at L over 2? And you could do that in algebraic form. So you had a algebraic expression for that. But that's now the process that you typically will go through, is figuring out what is this moment as a function of X. And I can just kind of relay that for this example problem. You can kind of see how that's getting confusing when you define M as a function of X, because you have other terms that are being multiplied by X. And so we generally drop that whole notion that V of X and M of X to represent them as functions of X. And we'll replace that with V1, V2, V3, same thing, M1, M2, M3. And we just know that M1, M2, and M3, they're all functions of X. And then it makes that a little cleaner, so we don't cause confusion with our expressions there. Does that make sense, Jordan?
Yeah, that's pretty clear.
And then you kind of saw that pathway for solving those more complex problems. I think even when I'd have a situation where there's a triangular distributed load, it's probably a little easier from my thought process to draw your free body diagrams and figure out what your internal moment is as a function of X, as opposed to starting back all the way from the beginning and integrating through. It might not be that simple to integrate all the way back through if it's got a complicated geometry. It's easier to figure out what your internal moment is as a function of X for each section of your beam. Because anytime you have a new loading showing up along the length of your beam, you really have to do this process for each segment of the beam. And then the continuity really just establishes that the displacement and the slope have to be equal along those points where there's a new loading applied, or there's a boundary condition that's within the center span of the beam. So that's what we'll be getting to on Wednesday next week, looking at making use of continuity, compatibility, and making up multiple sets of equations and solving for the boundary conditions based on those, solving for the constants of integration based on those boundary conditions, and now the continuity conditions included in that as well. But that's all I had for today. Do you have any other questions at all, Jordan?
No, I don't think so. I was just quickly looking at some of the homework problems just in the chapter 12 section, just to see if I could find anything that confused me. But everything looks really simple. I was glad to see that there's no crazy equations on those distributed loads in those problems. That makes me feel a little better.
Yeah, because you can get really complicated on the mathematics side, but it doesn't really help on the fundamental understanding, I don't think. So we'll kind of keep it as straightforward as possible. so we can understand the fundamentals. And when we start getting to more complex loading, I can show you some superposition techniques that still allow you to solve that in a simple manner without having to take 2 hours to solve a problem. We can make use of tables and superposition to solve those a little bit easier.
Okay.
So I think we'll call that good for today. And then we'll see one another again on Wednesday, where we'll just continue on looking at the whole compatibility continuity thing. And we should be done with chapter 12 by the end of the week, so that we'll have that chapter 12 homework due not this Saturday, but next Saturday, so we can keep on schedule with our homework due every Saturday. But thanks for your time, and we'll see you on Wednesday.
See you on Wednesday.